Welcome to The Explainer. Today, we're going to uncover the absolutely bizarre but brilliant quantum secret that makes your smartphone's memory work at all.
All right, let's start with something you probably have in your hand or your pocket right now, your smartphone. I mean, it holds so much of our digital lives, right? And every single time you snap a picture or download an app, something pretty incredible is happening inside.
So where does that photo go? It doesn't just float off into the cloud. No, it's saved right there, onto a tiny gray microchip. And let's be honest, it looks, well, pretty boring. But don't let its appearance fool you. Because if we were to crack open that one little component, we'd find it's not one solid piece at all. It's actually a stack of 8 individual memory chiplets, all layered on top of each other, kind of like a microscopic skyscraper. Okay, but this is where things get really wild. If we zoom in even further, I'm talking a nanoscopic view of just one of those chiplets. What we'd see is just this massive, perfectly organized grid of memory cells. And the scale here, it's just staggering. You've got this grid stacked 100 layers tall. Then it's 40,000 columns wide and 50,000 rows deep. Do the math, that's billions of tiny little vaults, and each one is just sitting there, ready to store a piece of your data. So how does this work? The technology behind it all is called charge trap flash, and the basic idea is that each of those billions of cells has something called a charge trap. It's exactly what it sounds like. It stores your data by physically trapping and holding on to electrons. Okay, but think about that for a second. That presents a monumental engineering challenge, right? How on earth do you design billions of these nanoscopic cells to reliably trap just a handful of electrons and hold them there for years? Because if they leak out, guess what? Your files get corrupted. Poof, gone. So what was the solution? Well, the engineers came up with a pretty clever idea. They decided to surround that charge trap with special materials called dielectrics. You can just think of them as really, really powerful electrical insulators. Basically, they build a wall to stop those electrons from escaping. And this is a fantastic way to picture it. Imagine the charge trap is like a deep valley. The insulator, that dielectric material, forms the high, steep walls all around it. So when you move electrons into the trap, they're stuck down in the valley. There's just no easy way for them to get out. But wait. This really clever solution creates a brand new and seemingly impossible problem. I mean, if the walls are so perfect for keeping electrons in, how in the world do you get new electrons in or out when you need to write new data? Like, when you save a new photo. Right. And from the perspective of classical physics, the physics that governs our everyday world, this should be totally impossible. The problem is basically unsolvable. See, according to those classical rules, an electron just plain doesn't have enough energy to jump over that super high dielectric wall. The amount of sheer force you'd need to apply would be so immense, you'd literally destroy the memory cell trying to do it. So, what now? To solve this, we need a completely different set of rules. And that, my friends, is where the weird and wonderful world of quantum mechanics enters the picture. Okay. So in the quantum world, you have to forget about the idea of an electron as a tiny, solid ball. It's not like that. It's more like a fuzzy cloud of probability. It's a region of space where the electron is most likely to be found at any given moment. So here's the magic. Instead of trying to brute force that electron over the barrier, engineers apply a gentle positive voltage to a gate right above the trap. This voltage attracts the negatively charged electron, and it starts pulling its little probability cloud towards the barrier. Now, if that barrier is thin enough, the cloud actually stretches and spreads right across it. And that means there's now a very real, non-zero probability that the electron will just, appear on the other side. This amazing phenomenon is called quantum tunneling. The electron literally tunnels through the wall instead of climbing over it. And get this. This isn't some wacky, abstract theory. It's happening inside your phone every single time you save a file. And what's incredible is that engineers figured all this out using quantum mechanical equations that were developed all the way back in the 1920s. They calculated the exact specifications needed to make this impossible-sounding feat happen reliably, billions and billions of times over. And the precision required is it's mind-boggling. That dielectric barrier, the wall of our little valley, in each and every one of those billions of cells, is only 75 to 100 atoms thick.
Think about that. This is one of the smallest things humanity has ever managed to mass manufacture.
And that thickness, it has to be absolutely perfect. It's a real balancing act. If the wall were just a little bit thicker, you'd need a dangerously high voltage to make that tunneling happen, and you'd just fry the cell. But if it were any thinner, the electrons wouldn't be trapped securely and your data would just slowly leak out over time. Okay, so after all that mind-bending science, what does this actually mean for your photos and your messages? You know, the files that are sitting on your phone right this second.
Well, what it means is that even this incredible technology isn't perfect. It's not permanent. Those charge traps, they do slowly leak their electrons over time. In fact, after about a decade of just sitting there untouched, files can start to become corrupt. And that right there is why it is so important to always back up your important files. Seriously.
Look, you obviously don't need to understand quantum mechanics to save a photo, but isn't it just fascinating to know that it's happening? It's just a powerful reminder to stop and think about the incredible, invisible engineering that's all around us. The whole idea is simple, but the structure to make it work is unbelievably complex.